Okay, one last Gauss's law problem for this run of videos for chapter 22. And that is example 22-4, a solid sphere of charge. So your book states the problem this way. An electric charge Q, a total electric charge Q, is distributed uniformly throughout a non-conducting sphere of radius r0. Determine the electric field A outside the sphere, r greater than r0, and B inside the sphere, r is less than r0. So we have to do this problem in two separate parts. We want to find the electric field everywhere in space, both outside the sphere and inside the sphere. And the calculation is a little bit different for each of those two regions. So again, I'm going to change the notation that your book uses a little bit, just because it's so hard for me to write subscripts and things clearly. On this tablet, I'm going to call the radius of the sphere capital R, and the charge of that sphere is capital Q. And we know that the charge density, let me write it this way, charge density rho is going to be the charge per unit volume of that sphere, which is the charge divided by the volume of the sphere, which is 4/3 pi r. We want to know what is the electric field at some point. Let's start with r greater than r, so out here. If we pick some point out here in space, what do we know about the electric field? Well, we know that no matter where you look at a sphere from, if you travel around it in space, it looks the same. So the electric field can't be a function of theta and phi. If we're talking about, imagine ourselves in spherical coordinates, right? This is our origin. Theta is this angle down like this. Phi is this angle around like this. If I look at a sphere from different places as I change theta and phi, I know that the electric field can't change because of the symmetry of the situation. So I know that out here, it must be true that the electric field is in the radial direction, and that it's only a function of r. So E is a function of r, E equals some function of r in the radial direction in spherical coordinates. Hopefully it's obvious that the Gaussian surface I should choose to wrap around this sphere is another sphere, an imaginary sphere in space that is concentric with my sphere of charge, so that everywhere on this surface, we'll call it A, the electric field is both constant and perpendicular. So on this surface, E is perpendicular to A, and E is constant. It's that perpendicularness and that constantness that allows me to actually do the integral that Gauss's law needs me to do. So we know from Gauss's law that the integral of the electric field over this closed surface perpendicular to the area, or another way to phrase it is the flux of the electric field through that closed surface, is equal to the enclosed charge divided by epsilon naught. What's the enclosed charge? Well, it's the whole charge of the sphere, because the whole sphere is inside of our surface. The electric field is the same everywhere on that sphere, so I can just write this as E times the integral of dA is equal to Q over epsilon naught. And once again, because we've chosen our surface carefully, the integral of dA doesn't involve any variables at all. And this is just equal to the surface area of the sphere, which is 4 pi r squared, which gives us the electric field is equal to, what do we have left on the other side? We've got an epsilon naught, we've got a 4 pi So 1 over 4 pi epsilon naught times q divided by r squared, which, surprise, surprise, is just the electric field of a point particle via Coulomb's law. This should look very familiar. The electric field outside of a charged sphere doesn't look any different than if the whole sphere's mass was concentrated at a point at the origin. This shouldn't be surprising to us. We talked about this when we talked about gravitational fields, that we can consider the gravitational field of the Earth, the strength of that field here on the surface, is the same as if the entire mass of the Earth were concentrated at the center. Remember when we calculated g on the surface of the Earth, the distance we used between ourselves and the Earth was just the whole radius of the Earth from here to the center of the Earth. So this answer shouldn't be surprising, that the electric field outside of a sphere is the same as the electric field due to that much charge concentrated at the origin. Inside the sphere, the situation is a little bit different. So let me actually just erase all this. Back up. We still want to choose a sphere as our Gaussian surface. It is still true that the problem has a spherical symmetry, and it is still true that if we put a sphere inside the sphere, if we put an imaginary sphere inside the actual sphere, that the electric field everywhere should be perpendicular, and that the electric field should be constant everywhere on the field. Hopefully that's obvious, that the electric field inside is still radial. The symmetry of the problem doesn't allow there to be any theta or phi dependence. And the electric field is going to be radial, so it's perpendicular everywhere to our imaginary sphere that we've drawn here. So what's the difference? The only difference is that the charge enclosed in our surface, Q, is not the whole charge of the sphere. When we write down Gauss's law inside the sphere, the integral of E dot dA is equal to the charge enclosed divided by epsilon naught. And that charge enclosed is not the whole charge of the sphere. It is the ratio of the, well, it's just this much charge. It's just this charge here. That was bad. This charge here inside of our little imaginary Gaussian sphere. How much charge is that? Well, it's the charge density times the volume of that sphere, right? It's the charge density of the whole sphere, which is constant. Okay, your book was very careful to say that this is uniform, times the volume of the volume enclosed by our Gaussian surface, which is 4/3 pi r cubed, where r is the radius of our Gaussian surface. And we're choosing a surface some radius r from the center. Since the density is just 4/3 pi r cubed times the total charge, this is just going to be equal to the charge density times the ratio, that's wrong, write this again, the total charge times the ratio of r cubed of our Gaussian surface to r cubed of the whole sphere. If that's not obvious to you, pause the video and go through this calculation to show that the charge enclosed in this little surface of radius little r is equal to the total charge of the sphere times the ratio of the cubes of the radii of our two spheres. Hopefully that is kind of obvious. So, nothing on the left-hand side changes. Our electric field is still constant everywhere on our imaginary green sphere, or imagined Gaussian surface that we've drawn. So, E times the integral of dA is equal to Q times r cubed, the radius of our Gaussian surface, divided by r cubed, big R cubed, the radius of the whole sphere. This is just the surface area of that Gaussian surface, which is 4 pi r cubed. Oh, wrong. 4 pi r squared. And this gives us... Oh, I lost an epsilon naught over here somewhere. Epsilon naught. I'm so concerned with my volumes. I lost my little constant. So this gives us that the electric field is equal to, what have I got? I've got a 4 pi, so still 1 over 4 pi epsilon naught. We should be very used to seeing that fall out of these equations. Q, let's write the Q here, times, we got an r squared here on this side from the A, we've got an r cubed on this side. Actually, let's write it like this. Q over r cubed times r. So if you check my algebra there, I got my 1 over 4 pi epsilon 0, I got my total charge, radius of the sphere, and r, which is the radius of the Gaussian surface, where I am inside the sphere, where I put my little imaginary surface. So what this means is, inside the sphere, the electric field actually increases linearly with your distance from the origin. Your book actually makes a little graph like this, showing that if you're inside the sphere, that the relationship between the electric field and R is that inside the sphere, it increases linearly with R until you reach, I pushed a button on my stylus and things got a little crazy there. Increases linearly until you reach r equals the radius of the sphere. Okay? That's this expression. The electric field is a bunch of constants times r. And once you get to r and get outside the sphere, the answer is, well, I've erased it. The answer is 1 over 4 pi epsilon naught q over r squared, which is this decreasing power function that we recognize as the 1 over r squared law. So outside the sphere is proportional to 1 over r squared. Inside is proportional to r. Okay, and that's an important result. You'll see something very similar when you do the electric field of a cylinder, an infinitely long cylinder. That's probably one of the problems I'll give you for homework. So hopefully we've learned how to do a few simple examples of Gauss's law. And like I said at the beginning, there's only so many of these that we can do. There's only so many shapes that have the requisite amount of symmetry that you can concoct some kind of surface that the electric field is the same everywhere on the surface, and that the electric field is perpendicular to the surface everywhere. So I'll give you the long uniformly charged cylinder for homework. I'll give you a cylinder inside of another cylinder where you have to find the electric field inside the first cylinder and then in the gap and then inside the second cylinder. But there's only a few more problems that one can actually use Gauss's law to find the electric field. Like I said, in some more advanced courses, we might see how to use Gauss's law to analyze an electric field if we know the electric field already. But to actually using Gauss's law to find the electric field, you're kind of limited to just a few very, very simple mathematical cases. So I'll go ahead and stop that there. I'll post some homework problems about Gauss's law, and then we'll probably go on to chapter 23.